much better informed the advanced stage. And so when we think about sort of the Earth system, sort of the scale and how different systems are connected to each other, the typical diagram is this. This is what's called the Bretherton diagram. It sort of shows different boxes of different systems and how they're related. And when you look at this picture from the perspective of thermodynamics and entropy, well, associated with entropy is the second law of thermodynamics, right? And the second law of thermodynamics gives you a very clear direction into which things should go. And you look at this diagram and you see that arrows go in both directions. So, to me, this is sort of, how does it fit together? And so, what I want to show you today is to basically look at this system from the perspective of thermodynamics. So, what do we do? Well, actually, we can start by asking why do things happen on Earth, and then we can, well, the longer you discuss things, the closer you get to the answer that it has something to do with the second law of thermodynamics. So, and what I will show you is that it gives a direction for Earth system processes. It sets limits to energy conversions, and that's specifically important for actually generating work. And because you need to have work when you have like motion in the atmosphere, you need to perform work to have motion against friction, because friction would always slow it down. And this connection to work, I think the best picture to illustrate this is actually a power plant. So when you think about a power plant that generates electricity, it's sort of a prime example for the second law and for energy conversions, because it converts heat by combustion into electricity, and with the electricity you can perform work. You can generate light, or you can give lectures, or you can heat your room, or you can cool your room, or you can cook, and so you can perform work. And what I'm going to do is, so I'm going to talk about how work is involved in Earth system processes, and I'm going to approach it with a specific additional constraint that processes actually work as hard as they can. And when we assume that they work as hard as they can, then we can derive very simple implications of relatively simple models for climate, how we can understand temperature and patterns on the land surface. And limits are of very different nature. One is that one can see, it's visible light, the other one is not so visible. And what this actually encapsulates that solar radiation is in the visible range is because it was emitted at a very high temperature, at the sun's emission temperature of about 5,500 degrees centigrade. And when you think about thermodynamics, that you have an energy flux and divided by temperature, then you typically have an entropy flux. And because you divide by temperature, actually solar radiation represents how a power plant generates work. It is by having heat coming in at a high temperature, at the combustion temperature. On the other hand, we have heat being exported from the power plant here in the form of this cloud you can see from the cooling tower, but this is heat at a much colder temperature from this approach. There are two other mechanisms that can use solar radiation and derive work from solar radiation. This is photosynthesis and photovoltaics. They are quite different processes. This thermodynamic picture and how it relates to work to different systems. Climate, so how thermodynamics constrains motion and thereby determines temperature. Applied to hydrologic cycling, how it shapes evaporation. To apply to life in terms of how it constrains photosynthesis. Basically, we have a state of disequilibrium that's generated because the solar radiation is mostly absorbed at the surface, while the radiation that cools the planet is emitted from the atmosphere. And so that sets up a temperature difference. Yeah? So the temperatures are warmer than the atmosphere, and that temperature can be utilized by this power plant. It can generate work, it can drive motion, in this form convective motion, convective motion then sustains turbulent heat fluxes. This is the most that one can derive work from. And then we have these temperatures. And what we now need to consider is the context in which this power plant operates. Because the more motion is generated, it generates more heat fluxes. And the more heat fluxes, the cooler the surface temperature. This is like, if you have hot soup and you blow over the soup and it cools, right? And so when you have convective motion, your surface is being cooled, and that means that this temperature difference here is going to decrease. And we can express this physically by considering